Hello, welcome to the AICE Chemistry Lecture Series. Today we're going to go over Chapter 7.3, which is going to look at applying the oxidation number rules that we learned in 7.1 to specific elements in specific compounds, polyatomic ions, and other situations. So again, this is a continuation of the 7.2 lecture and the application of the rules for oxidation numbers. So if you haven't watched the 7.2 lecture, then I will definitely go back and watch a video. If you have your notes from 7.2, I will definitely keep them at hand so you can reference the rules as we go through these examples and through all of the different scenarios. So let's get started. Let's first look at what happens when we have a compound of a metal and a non-metal. So this is very simple, straightforward ionic compound type of situation. More specifically, a binary ionic compound. Binary simply means made of two elements. So binary is just what I mean, made of two elements. Essentially, when we say we have a binary ionic compound, we mean an ionic compound where there's no polyatomic ion, meaning both the cation and the anion in the ionic compound are going to be monoatomic or a single element. The metal is always going to have a positive oxidation number in this situation, while the non-metal has a negative oxidation number. And this is simply because of rule number 6 that we learned in 7.2. where we said that the element that is more electronegative is going to have the negative oxidation number. Well, metals are never more electronegative than non-metals, and so we are going to have the metal having the positive oxidation number and the non-metal the negative oxidation number. So let's look at an example for it. Here we have sodium oxide, Na2O. In sodium oxide, which is binary because it's just made of two elements, sodium and oxygen, there are no polyatomic ions. The sodium is a positive metal. It's going to be the positive oxidation number, while the oxygen is going to have the negative one because sodium is a metal, oxygen is the non-metal. So if we look at sodium here in rule 1, or rule 2, should I say, we saw that group 1 elements like sodium are going to have a +1 oxidation number. So this is simple application of rule 2, where group 1 elements, regardless of what they are, sodium, potassium, lithium, are always going to have a +1 oxidation number. So this part of it is very simple and straightforward. On the other hand, oxygen here, which is the more electronegative element in the pair, is going to have the negative oxidation number. And with sodium, we saw, and I'm going to bring back the rules from the last one. With oxygen, we saw that oxygen is always going to have a -2 oxidation number, except for in peroxides, where it's -1, and in F2O, where it's +2. Because this particular situation is neither an peroxide nor F2O, our oxygen here is going to have a -2 oxidation number. So this is very straightforward and simple application of the rules that we saw in the previous video. If we keep going, if we do not know the oxidation number of one of the elements, however, so here we had a rule for both sodium and oxygen, but if we didn't have a rule for one of the elements, we can always find it by using Rule 5 in the previous video, in 7.2. Rule 5 said that when we add up the oxidation numbers of the elements, we need to have the overall charge of the ion, if it's a polyatomic ion, or 0 if it's a compound, be equal to the addition of the oxidation numbers. So for example, let's look at MgS. MgS, magnesium sulfide, is a binary ionic compound. As such, our metal, magnesium, is going to have a positive oxidation number, and sulfur, the anion, the non-metal, is going to have a negative oxidation number. If we look back again at the rules, we have rules for group 1 and group 2 elements, hydrogen, oxygen, and fluorine. Magnesium has a rule being a group 2 element. Magnesium being a group 2 element is always going to have an oxidation number of +2. But sulfur does not have a specific rule. The rule for oxygens do not apply to sulfur necessarily because sulfur is not oxygen. The rule we saw was specifically for oxygen, not for its whole group. So while we have a rule for magnesium, it's going to be 2 plus, we do not have one for sulfur. So looking at this, we can go back here and we know magnesium needs to have a +2 oxidation number. But we don't know what sulfur's oxidation number is. However, because of rule 5 and 4 in the previous video, we know that the addition of the oxidation number of magnesium and sulfur should add up to 0 because this compound is neutral. There is no charge for this compound. And we know that the oxidation numbers, when they're added between two of the elements in a compound, should add up to the charge of that compound or polyatomic ion. So if magnesium is +2, there's only one magnesium and one sulfur, and they need to add up to 0, then sulfur's oxidation number has to be -2. Not because there's a rule that tells us that sulfur has to be -2, but because there's a rule that tells us that the addition of their oxidation numbers has to add up to 0 since this is a neutral compound. And so +2 plus -2 is equal to 0. And that's going to be our oxidation numbers for this magnesium and sulfur. So both of these are examples of what we can do when we're faced with binary ionic compounds. Either both of the elements will have a rule associated with them, like sodium and oxygen, or we will have a rule for one of the two elements, like here with magnesium, and then we'll figure out the other element, like sulfur, by using rule number 4 or 5, where we use the addition of the oxidation numbers, which have to be equal to, in this case, 0, because this is a neutral compound. But what happens when we have covalent compounds made out of only nonmetals? If we have covalent compounds made out of only nonmetals, so a nonmetal with a nonmetal, in a compound containing two nonmetals, the more electronegative of the two nonmetals will always get the negative oxidation number. Now, we don't have to worry too much about this. This rule's always going to come true solely based on the application of the other rules. The addition of the oxidation numbers though, should always add up to 0 because we're looking at a compound. Compound, by definitions, have to be neutral in charge. So compounds are always neutral in charge, so the oxidation numbers always add up to 0. If it wasn't neutral in charge, not that that's not possible, is that it wouldn't be a compound. At that point, it would be an polyatomic ion. So let's look at an example of this. Let's say we have sulfur dioxide, SO2. Well, in sulfur dioxide, again, we have a rule for oxygen. We have said that oxygen is always going to be neutral. Oxygen is always going to be -2, except for in peroxides where it's -1 and F2O where it's +2. Well, if oxygen is always going to be -2, except for those two situations, and this is not a peroxide because it's not hydrogen peroxide and it's not F2O, then this oxygen has to be -2. However, there are two of these oxygens. Each oxygen is -2 or has a -2 oxidation number. In order to find out the sulfur, we have to remember that the addition of the oxidation number of sulfur plus the oxidation number from all of the oxygens has to add up to 0. Well, if we look at this particular example, we have oxygen having a -2 charge or oxidation number, and there are two oxygens, meaning that in total this has a -4 oxidation number. If the oxidation number of the oxygens have to cancel out with that of the sulfur to equal 0, that means sulfur has a +4 oxidation number. Again, this +4 does not come from a rule per se for sulfur specifically. It comes from the fact that the rule tells us that if a compound is neutral in charge, the addition of the oxidation numbers has to be equal to 0. And this is true of any case. For example, ICl3. In this particular case, we do not have a rule for either iodine or chlorine. However, we can make a simple assumption, because this is going to be one of those cases where a small assumption can go a long way. Now, this rule is still true. The addition of the oxidation number should always add up to 0. And additionally, because we know the more electronegative element is going to always get the negative oxidation number, we know chlorine is more likely to get the oxidation number, because chlorine is more electronegative than iodine. Well, we don't have a particular rule for chlorine per se. Chlorine is part of fluorine's group, meaning the oxidation number could be -1, which is going to be the case of chlorine if it's ever an ion, but we don't know that for sure. But having no clear rule to follow here, we can make the simple assumption that the chlorine is going to be -1. If you have no other choice, if there are no rules to follow when you're doing these exercises, then you can make simple assumptions like this, but make sure that those assumptions are based on concrete facts. Like the fact chlorine is more electronegative, so it's probably the -1. Like the fact that chlorine is a group 17 element, so more than likely we'll have a -1 oxidation number, because ionically, whenever it's an ionic compound, it has a -1 charge. Well, again, if we then follow this rule that it should have to 0, then if we know there are 3 chlorines and in total they're going to have a -1 oxidation number each, then we know that in total there is a -3 oxidation number for the chlorines. Well, if these need to add up to 0 and there's only 1 iodine, then iodine must be +3. Now let's look at one more interesting type of situation. If we have something like this, N2H4, where we have 2 of the nitrogens and 4 of the hydrogens, if we look at our rules, we actually have a rule for hydrogen, but not for nitrogen. If we look at our rules, hydrogen is always going to be +1 in oxidation number, except for when it's in a metal hydride, when the oxidation number will be -1. Again, a metal hydride just means a metal and hydrogen compound. So if we look at our compound that we're working, we have nitrogen paired up with hydrogen. Nitrogen is a non-metal, not a metal, meaning that this hydrogen should have an oxidation number of +1. That +1 oxidation number for hydrogen is the key to find the oxidation number of nitrogen. Why? Remember that if we have a neutral compound, the oxidation numbers for both the elements should add up to 0. But again, that means that this +1 times 4, which is only +4 in total, needs to be cancelled out by the oxidation numbers for nitrogen. Meaning that in total, the oxidation numbers for nitrogen should add up to -4. Because -4 plus +4 gives us that 0 that we're looking for. Well, if that's the case, if the nitrogen oxidation numbers need to add up to -4, but we have 2 nitrogens here, then each nitrogen should have an oxidation number of -2. Because -2 times the 2 nitrogens gives us that -4. So the oxidation number for each nitrogen, because remember, oxidation numbers are given per atom of the element, meaning per each one of these nitrogens, then the oxidation number of the nitrogen will be -2. Now we do have one more situation that we can look at. So let's look at this last type of situation we're going to have, which is what we call compound ions. Now, compound ions are what we call in honors chemistry polyatomic ions. Polyatomic ions are simply just ions made up of multiple elements covalently bonded together. So whenever we talk about a compound ion or polyatomic ion, we're essentially talking about a molecule with a charge. In a compound ion, we have to remember that essentially everything we do is exactly the same as we do it with compounds. But instead of the oxidation numbers adding up to 0, they will add up to the charge of the compound ion. So we're not adding everything up to 0, we're adding everything up to the compound ion's charge. So let's look at an example of this with nitrate. Now nitrate is NO3 minus 1. We're going to treat this exactly the same as we did a compound, only when we add up the oxidation numbers of the nitrogens and the oxygens, we should get -1 instead of 0. So oxygen, we already said that the rule is they're always -2 unless it's a peroxide or F2O, which this is not the case. So we know this oxygen is going to be -2. Now there are 3 of these oxygens. So in total, the oxidation number of all the oxygens added up is going to be -6. When we look at this oxidation number, and we're trying to find the oxidation number for nitrogen, we had to remember that when this adds up, it's going to add up to not 0, but -1. So when we add up the nitrogen oxidation numbers to those of oxygen, we should not be canceling out completely. We should be adding this up to -1. Meaning that in order for that to make sense, the oxidation number of nitrogen needs to be +5. Why +5? Because 5 plus -6 is equal to -1, which is the oxidation number or the overall charge for the polyatomic ion. So essentially, we're doing the same thing that we do with the compounds. They're just not adding up to 0. We're going to add up to the charge. So let's look at another example here. If we have the dichromate ion, again, everything is basically the same. Now, you're going to be seeing oxygen a lot like you're in these examples because oxygen is present in a lot of compounds and is also present in a lot of polyatomic ions. A lot of polyatomic anions are what we call oxyanions, meaning that they have oxygen in them. But again, we're going to follow the same example here. We have Cr2O4. We know oxygen, it is not peroxide, this is not F2O. So oxygen here has to be -2 in total, in oxidation number. Because there are 4 oxygens, a total of a -8 oxidation number. Well, that -8 oxidation number has to add up with the chromium oxidation numbers so that it gives us a total of -2. Again, this is because the total of the oxidation numbers added up has to be equal to the charge of the ion. Now, here we have 2 chromiums. In order for the oxidation numbers of the oxygens to add up to a -2, then we need for the chromium oxidation numbers to add up to a +6, because +6 plus -8 gives us -2 in total. If the chromiums overall have to be +6 and there are 2 of them, then each chromium needs to be +3. Because +3 for each chromium times 2 chromiums gives us +6, and then -2 for each oxygen times 4 oxygens gives us -8. 6 plus -8 gives us a -2 overall charge. And so that's how we assign the +3 oxidation number to chromium and the -2 oxidation number to oxygen. So this is the application and the 3 different kind of situations you're going to encounter for the application of oxidation states / oxidation numbers, whichever one you want to call them. So let's look at an example from the Cambridge exam. This is a question from paper 2. When magnesium is heated in air, magnesium oxide, MgO, is a major product. Smaller amounts of magnesium nitride, MgN3N2, is also made. Interesting information. We don't necessarily need this information, though, to answer this question. Because if we read the question, it says, calculate the oxidation number for magnesium and for nitrogen species in Mg3N2 to complete table 1.1. So this is a 1-point question where we have 2 boxes that we need to fill out in this chart. Meaning that if we don't get both of these completely correct, we will get no points because this question is only 1 point. Well, looking at this magnesium nitride compound, we need to figure out the oxidation number of magnesium and the oxidation number of nitrogen. Well, again, we need to remember our rules in order to do this properly. If I bring back the rules, there is no rule for nitrogen. However, because magnesium is a group 2 element, we know magnesium will be a +2 charge. Again, group 2 elements, according to rules, are always a +2 charge. So we know that magnesium here has to have a +2 oxidation number. Now, magnesium here is +2, and there are 3 magnesiums in total. That magnesium has to add up with the nitrogen oxidation number in order to give us, overall, a 0 oxidation number total. Why 0? Again, because this is a neutral compound. And because this is a neutral compound, the oxidation numbers have to cancel out. Now, that means that this oxidation numbers in total, +2 times 3 is going to be us +6. In order for these to completely cancel with the nitrogen oxidation numbers, the nitrogen oxidation numbers need to add up to -6. Well, in order to get -6, because there are 2 nitrogens, each nitrogen has to be -2, or sorry, -3 in oxidation number. Because 2 times -3 is -6. That -6 plus the +6 from the magnesiums gives us that general overall oxidation number of 0. Meaning that the nitrogen oxidation number has to be -3. And if we look at our mark scheme, that's exactly what we have. 2 plus, or plus Roman numeral 2, 3 minus, or -3. And that's our oxidation numbers. So these are the more straightforward questions where we would directly be asked to give the oxidation numbers of different elements in a compound. Later on, in later videos, we will look at how do we use these oxidation numbers in actual practice to then do other aspects of redox reactions. But that is it for today's video on section 7.3. Make sure you practice putting the oxidation numbers on these elements, on the compounds and polyatomic ions, because this is very much a skill that you need to practice, not something you just need to memorize. I will see you all in the next video.